When we look at Saturn, it appears as a study in perfect symmetry. It is an icon of the solar system, an image so clean and stable it looks almost artificial against the blackness of space. But that image hides a strange physical reality. This diagram illustrates the planet's density, or lack of it. Because it's composed primarily of hydrogen and helium, Saturn is less dense than water. If you could build a massive pool, this giant would actually float. That low density is a byproduct of how active the planet really is. Beneath that pale yellow haze, internal heat drives winds that reach 1,100 miles per hour, creating a volatile environment where gravity and gas pressure are in constant conflict. This tension between geometric stability and internal volatility is what defines the entire Saturnian system. It suggests that the same forces maintaining the planet's beauty are also powering the hidden oceans on its moons, the places where we are most likely to find life. The rings aren't solid disks. Up close, they are a blizzard of billions of icy fragments, constantly colliding as they orbit. The F-ring, seen here, is the most active part of the system. Sitting beyond the Roche limit, gravity is too intense for large moons to form. In these wavy regions, gravity tries to pull ice particles together, while sheer orbital speed smashes them apart. Embedded moonlets within the ring act like wrecking balls. When they crash into the ring's core, they create these visible fans and jets, disturbances in the dust stretching for thousands of miles. The F-ring is proof that what looks like a static, orderly structure is actually a site of near-constant destruction and reformation. That same balance between chaos and structure exists in the atmosphere, most famously in this six-sided storm at the North Pole. This isn't just a circular hurricane, it's a barotropic instability. It happens when the speed of the wind changes so sharply at different latitudes that the flow is forced to buckle into a wavy pattern. A massive jet stream is trapped between the polar vortex and slower-moving outer air. As these currents rub, tension forces the jet into 6 distinct corners. The pressure is so consistent, this shape remains locked in place for decades, rotating like a solid gear. It is a structure that seems impossible in a fluid environment, a sharp geometric shape held together by nothing but the relentless speed of the storm. These same physical stresses, gravity, pressure, and internal heat, extend to Saturn's moons. On Titan, the dense atmosphere supports a landscape that is eerily familiar, featuring mountains, dunes, and lakes of liquid methane. Sunlight breaks down methane in the upper atmosphere, creating a haze of complex organic molecules that rain down onto the surface. This cycle suggests that beneath the frozen crust, Titan may host a vast liquid water ocean enriched by these same organic chemicals. Then there is Enceladus. Its south pole features tiger stripe fractures, where Saturn's gravity creates internal friction, melting the ice from the inside out. The resulting plumes blast liquid water, salts, and organic molecules directly into space at over 400 meters per second. This cross-section shows the source. At the ocean floor, water interacts with a rocky core heated by tidal forces. This hydrothermal activity creates a source of chemical energy, the same kind that life uses to survive in Earth's deep oceans. Because these plumes bring ocean material directly to the surface, Enceladus has become our most accessible laboratory for astrobiology. We don't have to drill through the ice. The moon is already providing us with the samples. We have this data because of the Cassini-Huygens mission. For 13 years, this spacecraft served as our eyes and ears at Saturn, surviving the rings and mapping the moons with incredible precision. But as the mission reached its end, the discoveries at Enceladus created a dilemma. If the spacecraft ran out of fuel and crashed into one of these moons, it could contaminate a potentially life-harboring ocean with microbes from Earth. To prevent that, scientists chose a destructive end. They navigated Cassini into Saturn's atmosphere, where it disintegrated under the intense pressure it spent years studying. This was a final act of preservation, a choice to destroy our own technology rather than risk compromising the native environments we hope to one day understand. Saturn teaches us that beauty and the potential for life aren't found in a state of static perfection. They emerge from a dynamic, chaotic balance between gravity, wind, and heat. If you want to keep exploring the deep cosmos with us, make sure to hit subscribe. Until next time, keep looking up.